Hi everyone, it's Miss Berry again. Today in this video we are going to be going over section 4.2, which is called Addition Rules for Probability. We're going to get a couple of definitions and then one formula in this section. So make sure that you have something to write with so that you can write that stuff down. And then if you're not already, you should go and follow along with my guided notes that are available in our D2O. Alright, so let's get started. Alright, so before we get into any questions or formulas, I need to tell you some important properties of probabilities. The first property that I want you to be aware of is that all probabilities must be between 0 and 1. And then I've put the word inclusive here, so that means that it's 0 and 1 are included in that statement. So probabilities are allowed to be equal to 0. Probabilities are allowed to be equal to 1. But you just can't have anything that's less than 0 or negative, and you can't have anything that's greater than 1. Right, so all of your probabilities must be between 0 and 1. And then if you wanted to think of these as like percentages, you could change this to say like 0% and 100%. So probabilities have to be between 0% and 100% if you're thinking of them in terms of percents. Alright, and then our next property of probabilities is that the sum of all of the probabilities in your sample space should always add to 1. Alright, so if you list out all of the outcomes that are in a sample space and then you calculate the probability of each one of those outcomes, those probabilities should add up to 1. And then the probability of the empty set is 0. And remember, the empty set, that's the set that contains nothing. So this is just saying like, if you are trying to calculate the probability, if you are trying to calculate the probability of the empty set represents an event that cannot happen. So the probability of an impossible event would be 0. Alright, so our first definition that we have today, and we have some notation here, is called the complement of an event. The complement of an event E is denoted by E with a little c in the exponent. Different books use different notation for complement, so if you go on and take another stats class later, if you do any Googling, you might see that they use a different symbol for complement. But the complement of an event E is the set of all of the outcomes that are in the sample space that are not in E. Alright, so it's sort of, you can think of it as like the opposite. So if you're looking at a deck of cards, alright, so let's say that we're going to let R be the event of drawing a red card from a standard deck of playing cards. How would we describe our complement? That would be drawing a card that is not red. Now, in a standard deck of playing cards, the cards are black and red, so you could also word this as drawing a card that is black. Alright, so in a standard deck of playing cards, the cards are either red or black. So you could either say the complement of that event would be drawing a card that is not red, or just drawing a card that is black. Alright, so again, just notation stuff. If we're reading this out loud, I would call that E complement. Or in the case of our example that we just looked at, R with the little c in the exponent, we would call that R complement. You get to kind of think of it as like the opposite of R. The opposite of drawing a red card is drawing a black card. Alright, let's look at another example. Let E be the event of rolling an even number on a fair six-sided die. How would you describe E complement? What would be the opposite of rolling an even number? Rolling an odd number, right? Sorry, I skipped ahead accidentally. But the opposite of rolling an even number would be rolling an odd number. All right, so here's some examples with complement. It says, describe the complement of the event. The first event is choosing a vowel from the English alphabet. What would the complement or the opposite be of choosing a vowel from the English alphabet? That would be choosing a consonant from the English alphabet. All right, and then for number 1, part B, out of 82 students in our stats class, 33 are freshmen. All right, so what would be the complement of the freshman? Or what is the opposite of freshman? That would be a not a freshman, right? So that would be either a sophomore, a junior, or a senior. All right, so if 33 students are, if 33 students are freshmen, we would do 82 minus 33. Everybody that's left over is not a freshman. All right, so that's 49. All right, so out of the, I just tried to duplicate the wording here or replicate the wording. All right, so out of 82 students in our class, 49 are not freshmen. All right, and again, you could word this differently. You could say out of the 82 students in our class, 49 are either sophomores, juniors, or seniors. All right, so you could word that slightly differently if you preferred. Okay, a couple more examples. Part C says 53% of students at CCGA use AT&T. All right, so the opposite of 53%, we would do 100 minus 53 is, let's see, 7 and then 4. Is that right? Yes, 47. All right, so if 53% of students at CCGA are using AT&T, then 47% of students are not using AT&T. All right, and then this last one, a little bit harder because it's got some tricky wording here. It says 66% of 19-year-olds in our stats class are taking at least 12 credit hours. All right, so first we have to figure out what's the opposite of 66%. All right, so that would be 100 minus 66 would be 34. All right, so 34%, let me change my laser. 34% of 19-year-olds in our stats class are not taking at least 12 credit hours. All right, but I think we can word that a little bit better. So let's think about what the opposite of that is. So if you're taking at least 12 credit hours, that would be 12 or more. All right, so at least 12, that would be 12 or more. So the opposite of that would be less than 12. All right, does that make sense? So at least 12 credit hours means 12 credit hours or more. So the opposite of that would be on the other end of the spectrum, which would be less than 12 credit hours. So 34% of 19-year-olds in our stats class are taking less than 12 credit hours. All right, super easy one here. It says, find the number of outcomes in the complement of the given event. Out of 314 apartments at Coastal Place Apartments, 128 are currently available to rent. All right, so the number of outcomes in the complement. Well, first we need to think about what is the complement here. We're looking at apartments that are currently available. So the complement of that would be apartments that are not available to rent, or you could say like occupied. All right, so the complement here, we're looking at how many are not available to rent. All right, so you're just going to take your 314 minus 128. All right, so 314 minus 128 is 186. All right, so 186 apartments are not available to rent or are occupied, you could say. All right, a couple more easy examples and we'll get into our formula. Your computer science professor tells you that there is a 35% chance that you will fail the upcoming exam. What's the probability that you will pass the exam? Right, so those are opposites, right? So failing the exam versus passing the exam. So the opposite of 35%, that would be 100 minus 35 is 65. So if there's a 35% chance that we fail, there's a 65% chance that we pass. All right, this one's a little bit harder. It says, given that every 7th person in line at the movies will receive a free box of popcorn, what's the probability that you don't get a coupon when you're in line? All right, so every 7th person in the line is going to get a coupon. All right, so imagine we have these people here. 1, 2, 3, 4, 5, 6, 7. Okay. This 7th person gets the coupon. So you had, in essence, a 1 out of 7 chance of getting a coupon, right? So 1 out of every 7 people gets a coupon. So the probability that I get the coupon is 1 out of 7. Right, so what is the probability that I don't get a coupon? That's what happens to every other person in line, right? So there's 6 people that don't get a coupon. So 1 minus 1 over 7 is 6 over 7. So the probability that I don't get the coupon is 6 over 7. All right, so 1 person gets a coupon. That means probability of getting a coupon is 1 out of 7. Everybody else, all the other 6 people, don't get a coupon. So the probability that I don't get the coupon is 6 out of 7. All right, so think of the complement as the opposite of that original event. All right, so here's the formula that I was talking about. We call this the addition rule for probabilities. Sometimes you'll hear it called like the OR rule. All right, and it says the probability of E or F, E and F are just events. You can imagine this is like rolling an even number, rolling an odd number. All right, so the probability of E or F is equal to the probability of E plus the probability of F. Very straightforward. So just add up, what's the probability of that first one? What's the probability of that second one? Then you have this extra piece at the end. It says minus the probability of E and F. All right, so let me explain what's going on here, why we have to subtract that bit off the end. All right, so I was thinking of this in terms of students earlier, and I was thinking like, I could go through and classify my students. Let's just make up a few names. Let's say like Jan, Eric, Layla, and Zach. All right, so maybe Jan is a freshman. Say Eric is also a freshman. And senior, junior. All right, so just randomly assign those. And then maybe Jan is majoring in biology. Eric, let's say math. Layla, let's say psychology. And then we'll do business for Zach. All right. All right, so just coming up with a little data set here. All right, so maybe I asked you to just count up. Let's forget the probabilities for a minute. Let's just count this up. Let's think freshman or biology major. So imagine I asked you to count up how many people in this class are freshmen or biology majors. All right, well, you would count up the number of people that are freshmen. You would add that to the number of people that are biology majors. But then we have some freshmen who are biology majors. So if we counted this up, this is what would happen. We would say, okay, let's look at our list and see how many are freshmen. All right, we've got 2 freshmen. How many out of our list are biology majors? Just 1. All right, so no other biology majors. So we have 1 biology major. But then 3 doesn't make sense, right? There's not even 3 freshmen in the class. If you added up 2 plus 1 is 3. There's not even 3 freshmen in the class, so that doesn't make sense. So you have to subtract off this middle piece, which we call the intersection, because we've counted them twice. Essentially, that's what's happened, is we've counted Jan twice. All right, so you subtract off the number of people that are freshmen and bio majors. All right, so we had one person who was a freshman and a biology major. So 2 plus 1 minus 1 is 2. All right, so we have, if we were just counting these up, not even thinking about probabilities, we would say, okay, there's 2 people in the class that are either freshmen or biology majors. All right, so that's why we subtract off that end piece, because whenever you add up those first 2 groups, you may end up counting some people twice. And so that last little bit accounts for that. All right, so make sure you get that formula down. And again, this is called the addition rule for probability, or the OR rule. All right, so here's our first example. It says, at the hospital in Brunswick, 7 out of 17 doctors are general practitioners, 4 out of 17 are under the age of 45, and then 2 are both general practitioners and under the age of 45. All right, so we've got 2 doctors who are general practitioners, and they're also under the age of 45. All right, so our question is, what's the probability that you are randomly assigned a general practitioner or a doctor who's under the age of 45? All right, so we need to assign some variables here. So I'm going to call general practitioners GP, and I'm going to call under the age of 45 U. All right, just to make it less writing for me. All right, so now I just need to copy down the formula. So probability of general practitioner or under the age of 45. So probability general practitioner or under 45 is going to be equal to the probability that they're general practitioner plus the probability that they're under 45, and then subtract off that overlapping part. All right, so you start by doing the probability that they're a general practitioner plus the probability that they're under 45 minus the probability that they're a general practitioner and under the age of 45. All right, and then all the numbers are right here for us to grab, so this one's super easy. The probability of being a general practitioner, again, thinking success over total, there are 7 out of 17 doctors that are general practitioners. All right, so 7 out of 17 are general practitioners. Under the age of 45, we said 4 out of 17 are under the age of 45. And then 2 doctors fall into this last category. There are 2 doctors who are general practitioners and under the age of 45. All right, so we subtract them off so we don't count them twice. We don't want any duplicates in our data when we're calculating these probabilities. All right, so when you have the same denominator, it's really easy to work with fractions. You just do the operations to the numerator and you keep the denominator the same. All right, so 7 plus 4 is 11, minus 2 is 9. So do the operation to the numerator, denominator is going to stay the same. So that's going to be 9 out of 17. So you have a 9 out of 17 chance of getting a doctor who is a general practitioner or under the age of 45. All right, another way that we can present these problems is in a table. All right, so we have a summary here of some data that I collected from students one semester. It says, this table summarizes the data collected in some semester from my statistics students. This is the year of study or your class level and their living situation. So did they live on campus or off campus? All right, so you can see in my table here, we had freshmen, sophomores, juniors, seniors. Of those class levels, 18 freshmen were living on campus, 15 freshmen were living off campus. 10 sophomores were living on campus, 23 sophomores off campus. 2 juniors on campus, 10 juniors off campus, 1 senior on campus, 3 seniors off campus. All right, so the first thing you're going to want to do when you get a table like this is go ahead and calculate all your totals. So that's what I'm going to do next. I'm just going to go in here and add an extra row and an extra column, and I'm going to calculate my totals. All right, so starting with my freshmen, 18 plus 15 is 33. All right, sophomores, 10 plus 23 is also 33. Juniors, 2 plus 10 is 12. Seniors, 1 plus 3 is 4. All right, now I'm totaling up the rows. So this is all the people that live on campus. 18 plus 10 plus 2 plus 1 is 31. And then 15 plus 23 plus 10 plus 13 is 51. All right, so now that I've totaled up my rows and my columns, I can get like the total sample size just by adding those up. All right, so they should add to the same value. So 31 and 51, that needs to add to the same value as 33 plus 33 plus 12 plus 4. Otherwise, you added something up wrong. All right, so if you add those up, that adds to 82. All right, so 31 plus 51 is 82. And then 33 plus 33, that'd be 66. Plus 4 would be 70, plus 12 is 82. Yeah, so both of those add up to 82. So perfect. So we know our sample size is 82. All right, so we've got quite a few questions associated with this table. It says, what's the probability that a student in this class was a sophomore? All right, so sophomore, probability of being a sophomore, again, think success over total. How many sophomores did I have? 33. And what was my sample size or my total? 82. So 33 over 82. All right, so that's a very straightforward probability calculation. Next, we're making it a little bit more complicated. It says, what's the probability that a student in this class was a senior and lived off campus? All right, so senior and live off campus. All right, so here's my seniors. All right, I'm going to highlight this. This was my seniors. And this is my live off campus. Not me picking the worst color possible. Alright, so this was my people that lived off campus. Alright, the overlap is my successes there. Alright, so there's my overlap. I had 3 seniors that lived off campus. Alright, so probability that a student was a senior and off campus was 3 out of my total number of students, so 3 out of 82. Alright, so when you're doing the and, you want to think that's kind of like the intersection of that row and that column. Alright, so the intersection of the senior column and the off-campus row. Alright, so here's my little table. I went ahead and copied over the probability, or excuse me, the totals. I went ahead and copied over the totals. And this one says, what's the probability that a student is a freshman or on campus? Alright, so we've got the or rule there. So remember our rule for or, we add up probability of freshman, probability of on campus, and then subtract off freshman and on campus. Did I say off campus? I meant to say on campus. All right, so I'm going to go ahead and assign some variables here. I'm going to let freshman be F. I'm going to let on campus just be ON, on. All right, so probability of freshman or on campus, that's going to be probability of a freshman plus probability of living on campus minus the probability that you were a freshman and on campus. So that way we're subtracting off any duplicates that we counted twice. All right, so let's grab these probabilities. Probability of being a freshman, we had 33 out of 82 were freshmen. Probability of being on campus, we had 31 out of 82 that were on campus. And then let's figure out how many people were freshmen and lived on campus. All right, so here's my freshmen. Here's my on campus. All right, so the intersection of that row and column is my successes. All right, so I had 18 out of 82 that were freshmen and lived on campus. All right, so again, super easy to do this computation because when your denominators are all the same, you just perform the operation to the numerator and keep the denominator the same. So 33 plus 31, that would be 64. All right, so 64 minus 18, that'd be 46. All right, so 46 out of 82. Now that can definitely be simplified. I don't know if it said whether it wanted to be simplified, but I know the homework likes you to simplify the answers. So let's see, 2 definitely goes into both of those. All right, so that would be 46 over 82 becomes 23 over 41. All right, so reducing that fraction, simplifying that fraction gets me to 23 over 41. All right, and then our last one for this table, what's the probability that a student lives off campus? All right, super easy. Probability of off campus, we're just thinking success over total. Our total number of students that lived off campus was 51, and our total was 82. Our sample size was 82. 51 over 82, that does not reduce. All right, so we leave that as it is. All right, the last thing I want to talk about before I let you go is mutually exclusive. So when you hear, they'll use this vocabulary word here, mutually exclusive. That means that the two events have no outcomes in common, or basically that those two things cannot occur at the same time. So here's some examples of things that are mutually exclusive or cannot occur at the same time. You cannot fail the first exam and pass the first exam at the same time, right? So those are mutually exclusive, right? So you could not be both of those at one time. There's no students that failed and passed the first exam. All right, another example, rolling an even number and rolling an odd number. There are no numbers that are both even and odd, so they have no outcomes in common. And then drawing a red card versus drawing a black card, those are mutually exclusive. They have no outcomes in common. There are no cards that are both red and black in a standard deck of playing cards. All right, so why do you care? Why does this matter? Because whenever you're using that addition rule for probability with mutually exclusive events, something is going to happen. And it's not a big deal, and if you don't even, you can really calculate the probabilities without even thinking about it. It'll take care of itself in the long run. But let me show you what's going to happen if you use the addition rule for mutually exclusive events. All right, so just a reminder at the top, when two events are mutually exclusive, that means they have no outcomes in common. All right, so here's a little example that I came up with. It says, suppose that you had a box of t-shirts, and in that box there were 15 t-shirts that were size large, 20 t-shirts that were mediums, and then 19 t-shirts that were size small. What is the probability that a randomly selected t-shirt is a large or a small? All right, so these are mutually exclusive events, right? So a t-shirt could not be a size large and a size small at the same time. All right, so watch what's going to happen. If we do the probability that the t-shirt is a large or a small, that would be the probability that it's a large plus the probability that it's a small minus the probability that it's a large and a small. All right, so again, let's just approach this like we don't know what's going to happen. First thing you would do is figure out the total number of t-shirts in the box. So that would be 15 plus 20 plus 19 is 44. All right, then I can write my probabilities. Probability of getting a large t-shirt, there's 15 out of 44 that are size large. And probability of small, there's 19 out of 44 that are size small. All right, but whenever we go to subtract off the probability that it's a large and a small, there's no t-shirts that are a size large and a size small at the same time. So that probability is going to end up being 0. All right, so what happens is that this essentially gets thrown away. So 0 out of 34 is 0. And that'll happen anytime the events are mutually exclusive. You'll see that that last bit of the formula that last bit of the formula where you're finding the and part ends up being 0. All right, so then you could finish this. 15 plus 19 is 34, so that would be 34 over 44, which would reduce to 17 over 22. All right, so basically, to make a short story long, as my advisor used to say, if you have mutually exclusive events, this last bit of the formula is going to end up being 0, but no big deal. All right, guys, if you have any questions, please let me know. Otherwise, I'll see you in the next video. Have a good one.